Now we are moving on to the technical session. Today's session is on the topic Strange and Beautiful World of Quantum Mechanics, which will be delivered by Professor Sebastian. Now I invite Dr. Joby Thomas, former Vice Principal, St. Thomas College, Thrissur, to chair the session and to introduce the resource person. Over to you, sir.
Thank you, Sindha. Honorable Vice Chancellor, Professor K. Jairaj, the plenary speaker of the day, Professor K. Sebastian, Professor M. P. Kannan, Dr. Anish, Dr. Prashant, the head of the department, Dr. Sindhu, Dr. Joshi CL, Dr. Anthony Joseph, Dr. Savita, and the new faculty members in the DNSC, Dr. Shibu, Dr. Digisha, Dr. Kishore, and the participants. Warm good morning to all. At the outset, I would like to thank the DNSC, especially Dr. Sindhu and Dr. Shibu, for inviting me to chair this session because it is an honor for me. As Vice Chancellor mentioned, it's a new department, DNSC, not a new one. For the past 1 decade, the department is striving hard to establish under the leadership of Dr. Sindhu. I know she has took a lot of effort to establish the department. Now, after coming the new 3 faculty members in the department, they are doing very well to improve the academics and research in the department. Congratulations to the DNSC faculty team. My duty is to introduce and chair this session. I am not a person to chair Professor KLS because he is my teacher. But anyway, as you are aware, Professor K.L. Sebastian is an eminent professor, a pioneer researcher in the area of quantum mechanics. He has completed his BSc and MSc from Kerala and Calicut University respectively, and he is the first rank holder in the MSc program at Calicut University Chemistry Department. I think Professor M. P. Kannan was also there in that batch. They shared the first and second ranks for the MSc program. Immediately after MSc from Calicut University, he moved to Indian Institute of Science, Bangalore. Both Professor M. P. Kannan as well as Professor KLS for their PhD program. Professor KLS completed his PhD in the year 1976. Then he started his career in the Department of Chemistry of University of Calicut in the same year, 1976. He has served the department up to 1984. In 84, Professor Kailas moved to the Cochin University and served there as professor up to 1996. When he was in Cochin University, he received the prestigious Chandiswarup Bhatnagar Award in the year 1995. I think very few persons received Chandiswarup Bhatnagar Prize who was working in a university department. And Professor Kyle is one among them. Then in 1996, he has moved to Indian Institute of Science, Bangalore. And later, during his last period of services, he moved to the newborn IIT Calicut, and has served for the past few years there. And now he has retired from service. He is a recipient of so many awards. Chandiswarup Award. He is a fellow of Indian Academy of Sciences, Indian National Science Academy, J.C. Bose Fellow, and so many. And he was the associate editor of the famous journal Resonance, and also member of various editorial board members. And he has published more than actually Professor Kailas has joined. He is my teacher in the year 1988 when I was doing MPhil in the Department of Chemistry of University of Calicut. He was my teacher for the quantum mechanics as well as group theory. I taught these 2 subjects from Professor Kailas. since 1988, I have constant contact with Professor KLS while he was in COSAT, IIT. He has occasionally visiting our college, making and delivering lectures for the students. In various capacities, I know him very well. He's a very good teacher, very good teacher. Professor M.P. Kannan, Professor KLS, Professor Dr. Anish, all are very good teachers, Prashant also. Therefore, it will be very beneficial for the student community and participants. Okay, Professor KLS has joined.
Let us proceed. So I'll start by wishing you all a very good morning. The title actually is Strange and Beautiful World of Quantum Mechanics. And of course, this is given at the Department of Nanoscience and Technology at the Calicut University. As was mentioned, I was a former alumnus of the campus. Actually, one of the first students in the campus. So it is always a pleasure. I wish I had the opportunity to visit the university campus, but anyway, COVID is making it impossible. So I have to be in Cochin, in my home. It would have been nice to get back there and of course visit Professor Kannan. Anyway, I am a retired, something like 6-7 months ago, I retired from IIT Calicut after working at the Indian Institute of Science for a fairly long time. Yeah, I think this part I have already said. Department I have thanked, then HOD, then Dr. Shibu. So you see, the thing is, many of the slides you will find people from my hometown. My hometown is actually Pala, which is rather, I don't know what to say. Perhaps I should say famous or infamous, whichever way you look at it. These are the characters that I shall be using. This is Professor Captain Mathai Kudil. His house name actually suits him because you say he's a person who likes to drink. Then there is a professor whose name is Professor Quantum Ganidagatil. Then there are students like Neetu. Then there is a Lijo. These two are students. So first of all, you ask why quantum mechanics, particularly in nanoscience, why quantum mechanics? Well, the answer is very simple. It has been given by the Vice Chancellor. Quantum mechanics forms the basis for the whole of nanoscience. And of course, it forms the basis for chemistry and for a large part of physics. So it is a very important subject. Unfortunately, I will not be spending much time on nanoscience itself. I am sure the later speakers will be spending time with nanoscience itself. My aim is to talk to you about a little bit about quantum mechanics. And in fact, interestingly, there are two views on quantum mechanics, and these two views are shown here. One is actually, it is a very frightening subject. Something like this animation, there you see young people will not be familiar with this guy, but this guy is supposed to be Dracula, Count Dracula, the original vampire. And he is supposed to be a very frightening person. But what I would like to tell you is that, you see, this is not the way you have to think of quantum mechanics, at least in the 2-3 lectures that I have. I shall try to tell you that the subject is absolutely beautiful. It is just beautiful. How beautiful is it? Well, what I normally say is it is much more beautiful than the next picture that you are going to see. Okay. This is my personal opinion. It is much more beautiful than any film actress or anybody whom you may think of. Well, you see, I have been using this slide for a very long time. I have shown it to the UG students in the Indian Institute of Science. And once after my lecture was over, one of the students came and told me, "Sir, your slides are interesting, but your knowledge of films needs to be updated." So therefore, I wondered why he was saying that, and then I realized why, and so I changed this picture. So this is the updated picture, and what I assure you is that this subject is much more beautiful than any of the film actresses, beautiful film actresses that you would normally think of. Okay. So here is an outline of my talk. You see, if you think of microscopic objects like electrons, neutrons, protons, atoms, helium atoms, whatever atom you have, they all have a dual nature. They have a wave nature and they also have a particle nature. And this sounds very strange. How can something have a wave nature and a particle nature? The same object, how is it possible? That I will illustrate using what are known as the two-slit experiments. We will come to that. Then I shall spend a little bit of time on the uncertainty principle. And then I shall spend quite a bit of time on what are known as standing waves, because they are very important for the chemists. They are very useful in understanding atomic orbitals. In fact, we will be led directly to the concept of stationary states. And then I shall have this puzzling question: do we understand quantum mechanics? Well, the fact that I have put this question on a slide implies that the answer definitely has to be no. And in some sense, the answer is no. We don't understand it fully, but it is very interesting. And I'll also tell you the reason why I say that we don't understand it fully. Then I shall talk about what is known as the path integral, a very modern approach to quantum mechanics. And I hope I shall get time to cover all this. So let me start with two-slit experiments. So we will have a two-slit experiment. We will imagine that it is done with bullets. Why bullets? Because bullets are particles. That is the reason why we do this experiment with bullets. Okay. So this is a two-slit experiment. You have two slits. You can. Sorry about that. You have two slits here, and there is a source of bullets. The source of bullets, of course, is a gun, and you have a backstop at the back of the two holes or two slits. And just to make the experiment interesting, I will assume that this person is drunk so that he doesn't shoot out bullets in the same direction, but he shoots out bullets in random directions. So what is going to happen is, I will imagine, of course, this is an imaginary experiment. I will imagine that this guy is given 5,000 or maybe a lakh of bullets, and he is asked to shoot out all these bullets, and maybe 5,000 of them would have passed through these two slits, and they will be hitting the backstop. And so after he has done that, what we will do is we will go and examine the marks that are there on this backstop, this brick wall, which I refer to as the backstop. And then, of course, what I will do is I will make a plot of the intensity distribution of these bullets, the points of arrival on the backstop, and I shall get a curve. And that is what we normally do in science. Whenever you do an experiment, you make a plot and try to understand the results. So that is what we will do. So you can see him shooting out bullets. Now imagine I keep only slit number 1 open. Slit number 2 is closed. So what will happen? The bullets will pass through only slit number 1 and they are going to hit the backstop somewhere in this region. It is also possible that a bullet may hit an edge and maybe it may end up arriving somewhere here. That is also possible. So therefore, if I plotted the intensity distribution, in this case where I keep only slit number 1 open, I shall get this curve. You will get a maximum somewhere here. And as you go away from there, the intensity decreases on either side. And I have called it I1. Why I1? Because I have kept only slit number 1 open. Similarly, if you kept only slit number 2 open, what would you expect? Well, you can all imagine what is going to happen. You will get a maximum somewhere here. And as you go away from the maximum on either side, the intensity will decrease. So that is exactly what will happen. This is the intensity distribution I2. I2 because I have kept only slit number 2 open. And so this is very easy to understand. We know this is all that will happen. And now suppose I keep both the slits open and repeat the experiment. What will be the result? The result is again very simple. You will get two peaks, one corresponding to arrival of particles which are passed through slit number 1 and the other one corresponding to particles which are passed through slit number 2. And so this is the resultant intensity distribution. Again, it is very easy to understand, and this is the way a particle would behave. This is what we expect. Okay. And now let me also tell you the following. If you wanted to calculate I12, the prescription is very simple. You say a bullet could have passed through slit number 1 and arrived at a point, or it could have passed through slit number 2 and arrived at that point. If it passed through slit number 1, intensity distribution is I1, while if it passed through slit number 2, the intensity distribution will be I2. And so the total intensity I12 must be the sum of I1 and I2, and that is extremely simple, very easy to understand. Okay. Now another thing that I want to tell you is, you see, bullets have this particular nature. They arrive in lumps. You get one bullet. If you are somewhere along at the backstop, you will find that one bullet is arriving, and then later another bullet is arriving, and so on. So therefore, bullets arrive in lumps. They arrive in lumps, and so bullets have lumpiness. And in fact, we will generalize and say that, you see, in the case of particles, I12 is, if you do a two-slit experiment, I12 is the sum of I1 and I2. That is the first thing. And the second thing is particles will arrive in lumps, 1, 2, 3, etc. You will never get half a particle. You always will get 1, 2, 3, etc. 100 bullets, 100 particles, and then the next possibility is only 101. There is nothing in between. So that is essentially a nature of particles. Now imagine I repeat this experiment with waves on the surface of water. For that, you can imagine that there is a large trough of water. Let me draw somewhere here. There is a large trough of water. And I will have a vibrating device going up and down on the surface of water here. And then what would have happened? Waves will be coming out, and I will put two slits. Okay, I need to draw quickly because I don't have time. So these are the two slits cutting the surface of water, and what will happen is that the waves that have been produced, they can go through slit number 1 or they can go through slit number 2, and then they will pass through these two slits. They are shown here. Okay, they are shown here. And what will happen? They will pass through the slit and be detected. Will produce a displacement along the backstop, and that you can measure. So imagine you keep only slit number 1 open. What will be the result? The result will be an intensity distribution which looks like this. It is rather similar to the case of bullets. And on the other hand, suppose you do an experiment where only slit number 2 is kept open, what will be the result? It is similar to what happened in the case of bullets. You get an intensity distribution with a maximum somewhere here, and we will call that I2. And now, interestingly, suppose you do an experiment where both the slits are kept open. What is the result? In the case of bullets, I know that I12 is the sum of I1 and I2. Would that be the case with waves? And interestingly, well, if that were the case, then of course you will get this kind of pattern, but that is not what actually happens if you did this experiment. If you did this experiment, you get a series of maxima and minima. You see that there are points at the backstop here or there where the intensity of the waves is very small. But there are also points here or points there where the intensity is large, intensities are maximum. So therefore you get a series of maxima and minima. And this is what is referred to as an interference pattern. So therefore, interestingly, waves exhibit the phenomenon of interference. And further, see, in the case of bullets, we had seen that there is the idea of lumpiness. They arrive in integral numbers, okay? But what I can do is, you see this object that is vibrating at this point, what I can do is I can cause it to be vibrating with a slightly larger amplitude, and then the intensity that I detect at this point will increase by a very small amount. So suppose in some units, you say that the original intensity at this point was 1 unit, I can easily change it to 1.001 simply by increasing the amplitude of vibration of the source. So therefore, there is no such a thing as lumpiness in the case of waves, whereas particles always have this lumpiness. Okay, so therefore we see that waves and particles are very different. And so in this case, I1 plus I2 is not equal to I12, and there is no lumpiness. So I have made an animation to demonstrate these ideas. What is going to happen is that you will see that there are waves incident. There is a wall here. Waves are incident on the wall from this side, and they will of course be reflected, but those reflected waves I am not showing in the animation. There is a slight opening here, and what will happen is that when waves are incident, these waves will pass through that slit and spread on the other side, and that is what you are going to see. Okay, as I said, the reflection from here is not shown because that will complicate the appearance of the animation, so I have not done it. So this is what happens, and you can place detector along any point along this line, and you will find that somewhere here you will get the maximum, and as you go away, the intensity will decrease. So similarly, suppose you have, okay, now in the case of waves, we actually know how to calculate the intensity. If you wanted to do it theoretically, we know how to calculate the intensity. How do you do that? The prescription is that you see intensity is proportional to the square of the displacement. See, for example, if the displacement at this point is in the upward direction, and if it is by 1 centimeter, then what you have to do is you have to take the square of that displacement. You may wonder why take the square. Well, you say displacement can be positive or negative, but the intensity is actually positive. So that is one reason, of course, but wave phenomena are like that. You have the displacement and then you take its magnitude and square it, you will get the intensity. And displacement, normally I should denote it by the symbol D because that is appropriate, but I shall change the notation for this lecture. I shall denote it by the letter psi1, psi. And I have put a subscript 1. Why did I put that? Because I am thinking of waves which have passed through slit number 1 because I have kept only that slit open. So therefore, you take the displacement at a particular point. When only slit number 1 is kept open, take its magnitude and square it. You will get a measure of the intensity. So that is the prescription. Now suppose I do the same experiment. Well, I should also remind you that this is true not only of waves on the surface of water, it is also true with electromagnetic waves. Now if you keep, there was a slit 1 here, but now I have only slit number 2 open and the waves will pass through that slit alone. The results are pretty much the same. And in this case, again, intensity, if you measure, you will find that it is a maximum somewhere here. And as you go away from there, the intensity will decrease. So that again is very obvious and clear. And if you wanted to calculate the intensity I2, you will say that, okay, I2 is, strictly speaking, I should have said the proportional, but what I have done is I have adjusted my units and so on in such a fashion that the square is simply, the proportionality constant is equal to 1. So therefore, I just put equality sign. And what is I2? So I2 is the displacement of the water surface at any particular point, at this particular point, when only slit number 2 is kept open. And now imagine I do the experiment again, keeping both the slits open, what will happen? This is what happens. You see, there are waves which are passing through slit number 1, passing through slit number 2. And if you place a detector at this location, you will find that there is almost no displacement of the water surface. But here you will find a large displacement, while if you are here, you will find very small displacement. And what is happening? Well, the answer is very simple. See, waves are passing through both the slits. So at this point, you see a wave from slit number 1 would arrive. And let me say it produces a downward displacement. At the same instant, the wave, the part of the wave has passed through slit number 2, and that will also arrive there. And let me say that that is a displacement that is produced in the opposite direction. So therefore, the displacements caused by the two waves are in opposite directions, and therefore they cancel each other, and therefore there is no net displacement. What I am saying is that if we added together psi1, that is a displacement due to the first wave, and psi2, that is a displacement due to the second wave, you get the net displacement psi1 plus psi2, and psi1 and psi2 cancel each other, and therefore there is very little displacement at this location. But at this point, at this location, psi1 and psi2 reinforce each other, and therefore you have a large displacement. And here again, they produce a net displacement of 0. So therefore, you see, if we plotted the intensity, what will happen? You will find that there is a minimum where right here where there is this destructive interference, and right here where there is destructive interference, and right here where there is constructive interference. The two waves add up and you get a large intensity, and therefore this is very easy to understand. And I12 is simply the square of the sum of these two quantities I1 and Psi2. So therefore we say I12 is actually Psi12 square. And how would you obtain Psi12? The answer is if you have kept two slits open, you have to think of the wave, contribution to the wave from slit 1 and contribution to the wave from slit number 2, and add them up, and then we will get the total wave. So instead of using displacement or wave, what I will do is I will refer to these things as the wave function. So therefore, in whenever you have whenever you have wave phenomenon, the idea is that you can associate what is referred to as a wave function, and what is the use of the wave function. The wave function is used to calculate the intensity. If you take the square of the magnitude of the wave function, you are going to get intensity. That is the first thing. Then you see, if you do a two-slit experiment, what happens is that there are two contributions to the wave function. Psi1 would be the contribution from the waves which are passed through slit number 1, and Psi2 would be the contribution from the waves which are passed through slit number 2. And you simply have to add up the two contributions and you will get the total wave function. And once you get the total wave function, take the magnitude and square it, you will get the intensity. And we understand all this. Now, what is your wave function? Well, in the case of waves on the surface of water, you can say that, okay, it is nothing but the displacement of the water surface, which can be positive or negative. Now, suppose with all this knowledge, I do a two-slit experiment with electrons. So here I have the experiment. This was done at the Hitachi company. The experimental arrangement is shown here. You have a very thin nanowire. Well, I shouldn't say nanowire, a very thin wire. Well, it is not nano size, but thicker. 1/1000 millimeters in thickness. And you have an electron gun which selects electrons having the same energy, and these electrons can pass through that side of the wire or through the other side of the wire. So therefore, you essentially have two ways in which the electrons could travel. And here the electrons will be detected, and this detector is extremely sensitive. That is why it was done at Hitachi company. They were the first to develop a detector which can detect even the arrival of a single electron. So therefore, the electrons will pass through this side or through that side perhaps, and will be detected at the detector. You can actually, the detector is sensitive, you can notice the arrival point of single electrons. And now in the next slide, you are going to see a video. The video is taken from this particular website, and it is a video published by the company. So you see, you will see the arrival points. There are different points of arrival, and oh, sorry, I mean, there is a little bit of problem. I have to go back. Okay, I am going to play this again. You will see that there are spots at the screen appearing. These are arrival points of single electrons. And what do you find? They seem to be arriving at random positions, right? There is no distribution that is clearly visible in this experiment as of now. And because you can see the arrival points, you will say that, okay, electrons are actually particles. Because that is a practical property. And still you don't see any pattern. You have collected together pattern from a large number of electrons, but the experimenter has continued. And now if you look carefully, you will see interference pattern. Correct? So you see, if you do this experiment with one or two electrons, what happens is that these two electrons seem to be arriving at random locations on the screen. Even with 100 electrons, that is the appearance. But if you have done this experiment with, let us say, 10,000 electrons, then what happens? You get this interference pattern that is visible on the screen. So then, the intensity distribution has an interference pattern. So therefore, what is the conclusion? The conclusion is that there must be a wave function associated with the electron. What is the use of the LED wave function? The use is that you take the magnitude of the wave function and square it, you will get the intensity. So therefore, the wave function is useful to calculate the intensity distribution of the electron. Now then you will also ask, suppose I do this experiment with a single electron. See, this experiment has been done. And I do this experiment with one more electron. Where will that electron go? Yeah, from our previous experience, we cannot say with certainty where that electron will go. It is impossible because it could have arrived at any location, maybe here or maybe there or maybe there, and so on. But then you can say that you see there is an interference pattern. So that means there are points where there is more likelihood of the electron arriving. Okay, see, for example, let me say here along this line, there are more electrons arriving in the multi-electron experiment. So if I did an experiment with a single electron, there is more chance that the electron would arrive there rather than the chance that the electron will arrive there. And therefore, you can say that, okay, the chance of the electron arrival is determined by what? The wave function. So in a multi-electron experiment involving large number of electrons, the square of the wave function will give you the intensity, while in an experiment with a single electron, the square of the wave function will give you the probability, strictly speaking, I should say probability density, that the electron will be arriving at that location. So that is our conclusion. So in a single experiment done with a single electron, it is impossible to say where the electron will arrive. All that you can say is, okay, these regions are more probable than others. And there are actually, okay, whatever I have told you is summarized in this slide. With electrons, we have already seen, we understand this, I1, I2 are the intensity distributions. Interestingly, this also I have said, when you detect them, you find them at specific locations, therefore they behave like bullets. And if they behave like bullets, this is the intensity distribution that you would expect, but that is not the intensity distribution that you find. You find the electrons, what you find is that the intensity distribution is an interference pattern, indicating that there is a wave associated with the electron and there must be a wave function. What is the use of the wave function? The wave function may be used to calculate the intensity. You take the magnitude and square it, you will get intensity, or in the case of a single electron, you will get the probability density that the electron will be found at that location. So electrons are like bullets. They are like particles, but they exhibit interference. So this experiment that I have told you about is actually published as a paper in the American Journal of Physics, seen here, in the year 1989. Yeah, well, this also I have told you how do you calculate I12, that I have told you. You have to take the psi12 and to take its square. And how do you get psi12? Answer is you add together contributions from the waves which are passed through slit number 1, which we denote by psi1, and the contribution from the waves which are passed through slit number 2. You add these two up and you will get psi12. Now you see, remember what I have told you. What I have told you is that in a single experiment with involving only a single electron, I cannot say where the electron will arrive. And I can only make probabilistic predictions. I can say there is a high chance that the electron will arrive at this location, while at another location, the chance is very small. And this is a fundamental nature of quantum physics. But Albert Einstein, one of the most famous scientists, was unhappy with this aspect of quantum mechanics. He said that in science, all predictions have to be definite. You cannot make a probabilistic prediction. And his feelings he expressed by this statement: God does not play the game of dice. By which what he meant was that he did not believe that quantum mechanics is the final complete theory. He thought that there is something more that is needed. But as of today, you see, there is no other theory that has been suggested. And it doesn't look like we need another theory at all, because all the experiments that we have done till today are in agreement with the principles of quantum mechanics, with the predictions of quantum mechanics. Now, historically speaking, you see, I have shown you this experiment with electrons, but historically speaking, this kind of behavior was observed first in the case of electromagnetic waves, in the case of light. So a little bit of history I shall have to hurry through. So Newton said light is a beam of particles, even though before him Huygens had suggested that light has a wave nature, because he pointed out that light exhibits interference. But you see, scientifically, Newton was considered to be a much bigger scientist, and therefore, when Newton came along and said light is a beam of particles, everybody threw out the theory of Huygens and believed Newton. And then later on, Maxwell came into the picture and he formulated what is known as the electromagnetic theory of light, which very solidly established the light has a wave nature. And then Einstein came along and pointed out that if you wanted to explain the phenomenon in a photoelectric effect, you have to assume that light behaves as if they are particles, as if they are bullets. So, and this was put on a solid basis on further solid basis by Compton, who did scattering of X-rays from a piece of metal, and he pointed out that in his scattering experiments, light is the X-rays behave like a beam of particles and not waves. So actually, this was the situation towards the end of the 19th century, and things were very confusing because on Mondays, Wednesdays, and Fridays, light seemed to behave like a particle, while on Tuesdays, Thursdays, and Saturdays, it is behaving like a wave. So naturally, the students will have this question, what about Sundays? Well, you see, that is because on Sundays, you don't normally do experiments. So what do? You may go to your place of worship, and this was the prayer of the scientists of those days. They would go to the place of worship and ask the Lord for a clarification. Is it a particle or is it a wave? But now we know that, you see, it is both. We know that it has a particle nature. It also has a wave nature. Because when you detect it, you are detecting a particle. But then when you do a two-slit experiment, you see it exhibits interference, which means that it is a wave. So therefore, we know that it has a dual nature. And interestingly, not only light, but everything in this universe seems to have this dual nature. Of course, saying everything is a big extrapolation, because we don't have experimental proof for everything. We have experimental proof for electrons, of course. We have proof for neutrons, protons, helium atoms, and even a big molecule like C60. It has been experimentally demonstrated that it has a wave nature. Okay, scientists are still attempting to do the two-slit experiment with bigger and bigger systems, bigger than C60. So here is the experiment done with C60. If you do not know what C60 is, it is just a cluster of 60 carbon atoms arranged in the form of a football. And the two-slit experiment was done by a scientist called Anton Zeilinger at the University of Vienna. This is actually in the absence of any slit, only one slit, so to say. And if you have two slits, I mean, this is strictly speaking, I should give you more details, but I don't have time. Anyway, the idea is that you get this interference pattern. So this clearly demonstrates that you can do this two-slit experiment with a big molecule like C60. Of course, you have to produce a beam of C60 molecules and do the experiment. That is not technically easy, but people have done it. And you get this interference pattern, which implies that C60 molecules have a wave associated with them. Okay. Now, not only has it been done with the C60, people have done this experiment with a rather big molecule, I mean, like phthalocyanine. So we will look at the experimental result in the next video. I am sorry, I am hearing other people speaking.
Excuse me, Dr. N. Shanmugam, can you please mute your...
Shibu, you do one thing. You ask the technical staff to mute all of this.
Yes. Hello?
Okay, sir, can continue.
whether I have been muted.
Okay, sir, continue.
Okay. So the thing is, you see, you have a phthalocyanin molecule, and you are going to see the result of a two-slit experiment done with phthalocyanin molecules. So you will see that there are spots on the screen. These spots are arrival points of a single phthalocyanin molecule, indicating that they are particles. But then when you have collected together a large number of arrival points of phthalocyanin molecules, here is the final result. And you can see clearly an interference pattern. Okay, so therefore this again demonstrates that a molecule like phthalocyanin has this dual nature. It has you can see the points of arrival, so that means they are like bullets. But at the same time, when you have collected together data from a large number of arrival points and plotted them, you get this interference pattern, which means that there is a wave associated with the molecules. Okay. Now, a very important aspect of this dual nature was suggested by de Broglie, and that is actually, you see, if you imagine you have a particle that is moving, and imagine that it is moving with a momentum p. This, of course, is a microscopic particle like an electron. Then what our experience tells us is that somehow there is a wave associated with that particle. And one of the most important characteristics of waves is the wavelength. See, for example, this length is what you refer to as the wavelength. So this wavelength is a characteristic, a major characteristic of the waves. And what de Broglie suggested was that this wavelength of the associated wave is determined by the momentum of the particle. Momentum p of the particle. And he suggested that the wavelength is inversely related to the momentum. So that was the suggestion that he made. And so he actually, in his PhD thesis, he made the suggestion that the wavelength is related to the momentum by this relationship, lambda is equal to h by p. And as I said, this was made in his PhD thesis, and the examiners did not believe him fully. And he would not have been given the PhD degree unless Einstein said there is maybe some truth in what he is saying, and therefore he should be given the degree. But later on, you see, people, de Broglie during his thesis defense predicted that it should be possible to see electron diffraction. It should be possible to diffract electrons from crystals, and that experimental, because the electrons have a wave associated with them, and that prediction was experimentally verified sometime later, and therefore this is now an established fact, lambda is equal to h by p.